Example 1. How does a potential electric field look like for a conducting sphere? So once we know how charge distribute the charge distribution, then we can use that as a tool to understand the potential and the field. So how does the potential and the field look like? We know that charge will evenly distributed around the sphere. So if we take that idea and study this case. So first, if I want to know the potential of electric field outside of the surface, then what is it going to look like? Outside of the surface, we can simplify the entire ball as a point. So we can just use the point charge potential and the point charge electric field to understand its distribution out of the ball. So if you look at the following two graphs, on the left-hand side, they tell you the electric field distribution, and the right-hand side is a potential distribution. And outside of this sphere, you will see the electric field, both the electric field and the potential, they will decay. And one decay as kq over r squared, another one decays as kq over r. All right. So that's a simple case. But how about inside the ball? What's going to happen? So we know inside the ball, the potential, the charge will move around until they reach equal potential. So the potential inside the sphere should be a constant. It's a constant, so which means the potential at the center of the ball are going to be the same as the potential on the surface of the ball. It will be the same value, we so-called V in or Vs. So exactly what is this potential? So this potential is nothing but kq over r, where r is the radius of the ball. So this is kind of makes sense because we know this potential RVS. This line, the center of any point inside the sphere will be the same on the has the same potential as the surface. And the potential of the surface, because we are on the surface, so we can just imagine the entire ball and shrunk everything into a point. Then we use the charge potential to calculate the potential on the surface of the ball. So it's kind of like a limit of the V out. And since the potential is the same everywhere inside the sphere, then the electric field must be zero. Because if there's any electric field, the charge will be pulled around because of this electric field. Otherwise, you can understand this zero electric field from a mathematical perspective. We know electric field is nothing but change of the potential over the displacement. Since there's no change of potential inside the sphere, then there will be no electric field as well. All right. So this chart and these two plots basically conclude everything qualitatively and quantitatively of what's happening in around a charge conducting sphere. Another case I want you to look at is the same question but on an insulating ball. What if the ball is an insulator? Again, the charge want to redistribute themselves so that they will feel happy and low potential. But remember, because of its insulating nature, the charge cannot really move freely in this ball. So a lot of them will still be trapped in the center. And because of that, if we look at the potential distribution and the electric field distribution, for the potential distribution, outside of the sphere is going to be the same because we can shrunk the entire ball into a point and use kq over r and kq over r squared. But inside the ball, you can see the potential will keep increasing as we move from the surface of the ball to the center of it. And it just takes a lot more energy, a lot more potential to move the charge from the surface to the center because they don't move and there are a lot more charges in the center. And because of that, the electric field inside this insulating ball will also increase linearly from 0 to the radius. To really understand what's the field look like in these two cases, it takes a little bit calculus, and we also need to understand the we so-called the Gaussian principle. So if you're interested in what's happening inside a non-conducting ball, you can go up and find more resources online or talk to me. And the third example, I'll basically use whatever we just talked about, and based on the first example and the conceptuals, I'll guide you through how to think about a quantitative question like this. So again, I have two balls. One carries 3 coulomb, one carries none, no charges. And when I bring them together and separate them, what's the new charge distribution look like? All right, so when I think about this question, let me count what physics I know here. I know what's gonna happen is these 3 coulomb will redistribute themselves among these 2 balls. So because charge cannot disappear, so whatever final charges I have, I don't care about the ratio. Eventually, the total charge should be the same. So that's my idea one. My second idea is I know when these two metallic balls they are brought together, they will share the same potential. So the potential of these two balls should be the same. So based on these two ideas, I listed two equations. One is the total charge is 3 coulomb. Another one is these two will share the same potential eventually. I know a little bit more about the potential because I know potential of the ball inside a ball is nothing but kq over r, where r is the radius. And because of that, the potential for the big one will be kq1 over 2. For the small one will be kq2 over 1. And they should be the same. Now let's look at these two equations. I have two equations with two variables, q1 and q2. Then I can solve these systems of equation. Then eventually I'll get q1 to be 2 coulomb and the q2 to be 1 coulomb. So here's the typo here. It's q2 to be 1 coulomb. So that's it. Basically, once you know the concept, you should be able to write down your thoughts in math and manipulate them till you get the answer. Lastly, I want to briefly talk about the application of this interesting idea. So, so far we talk about big size, small size of ball. But what if I have something that's not a ball? What if I have like a needles or something like this, where one end is more has a larger curvature and one end has a smaller curvature. So in this case, if you can see the charges, you will see charges will distributed around the surface, and when they reach the equal potential, you will see more charges on the left hand side and then less charges on the right hand side. But the charge density will be higher on the right hand side compared to the left hand side. So I'm going to briefly talk about the physics behind this. The charge density on the surface has something to do with its radius. So for example, I can model this irregular needle shape as two balls, a big one and a small one. So I know for the ball, on this ball, the charge density on the surface would be whatever charge we have over 4 pi r squared. So 4 pi r squared is the area. So Q over the area is the charge density. And where density for a ball is 4 pi r squared. All right. So how does that relate to the radius? So here I know a fact that because these two balls are brought into contact, they're connected together, so potential should be the same. If the potential should be the same, since V equals to KQ over R, if V is the same, K is a constant, then Q will be proportional to R. So now we know Q is proportional to R in the numerators, and the denominator is proportional to R squared. So after we cancel out one of the R from both sides, then we know that the charge density will be proportional to 1 over R. That being said, for the larger R, charge density will be smaller. So the charge density on the larger ball will be smaller, whereas the small ball, which has a smaller radius, that has a higher charge density. So this physics and math totally summarize what you see in the picture, where there's a higher charge density on the pointing edge and less charge density on the other end. And this is like the idea of this is like the design of lightning rod. In the lightning rod, if we know the cloud carries some charges because it has some frictions between them, and because of that charges, say if it carries positive charges, it's gonna attract the negative charges from the surface. And say if you have a house there, since your house is higher than the ground, so if there's a lightning, the charge will want to leak out from your house first. So some people like a smarter idea. They were like, why don't I just build something which is a little bit taller, like a lightning rod? If the lightning rod is mounted at a higher place, then whenever we create these charge separations, you will see a lot of electrons will be attracted to this lightning rod, and then it will be easier because the electric field, because now the tip of the rod is closer to the cloud. So in the same potential difference, I have a less I have less distance. So that creates a greater electric field. Greater electric field means the charges will want to leak out easily from this lightning rod. And also the shape of the lightning rod is also somewhat pointy. A more pointing shape will cause a higher charge density. If there's a lot of higher charge density, you can imagine this charge will want to, because it's too crowded at that end. So the charges, when we have when there's a choice, for the charges to leak out from the pointing end or more flat end, charges will always want to move out from this pointing end because it's too crowded. So basically, because of these two reasons, that's why you will see the lightning rod as it is nowadays. It is usually higher or taller at the top of your house, and it's also somewhat pointy. Okay, so but I think exactly why and how effective it is to have this lightning rod is still under a little bit scientific debate. So I don't want to tell you this is exactly the reason behind that. And people, of course, they are designing some better lightning rod that can help us to hide from this lightning. But this is a simple explanation that can help you sort of understand what's happening in a traditional lightning rod setup.